Geologist Consortium. I can describe the historical development of evidence that supports the plate tectonic theory. I can also relate plate tectonics to the formation of crustal features. Alfred Wegener proposed a theory based on observations and evidence he collected over decades. After his death, scientists continued to collect information which not only supported Wegener's beliefs, but expanded on them. Today, the theory of plate tectonics is the result of much of Wegener's work. Watch the video for more information on Wegener and his theory.
Take a look at this satellite image of Earth's surface. If you look carefully at the continents, you might notice something which many have noticed in the past, and that is that the continents almost look like they fit together, kind of like the pieces of some sort of giant, massive puzzle. Of course, you probably noticed this the very first time you saw a map of the Earth or a globe while a child in school. The place on the Earth where this is most obvious is along the eastern coast of South America and the western coast of Africa. Here it really appears like the continents fit together. Now, of course, people have known this for hundreds of years, ever since the first accurate maps were created. But most people just chalked it up to mere coincidence. One person who had trouble with that, though, was German meteorologist Alfred Wegener. You see, Wegener couldn't just accept that this was a coincidence and that these landmasses had such similar shaped coastlines. And so he began to think about this and try and come up with some sort of explanation. And what he concluded was something radical, that the continents are moving. And in Wegener's head, if the continents are in fact moving, and you run time backwards, there must have been a time when all of those continents were together in some sort of supercontinent, something he named Pangaea, coming from the Greek term for all Earth. This became known as Wegener's theory of continental drift. Now, Wegener, being a man of science, knew that if his theory was going to gain any traction, he needed to provide evidence. And so he set to his life's work of researching every corner of the planet to better understand this strange observation and to explain it to the scientific community. By the end of his life, he had collected 4 main pieces of evidence, and we're going to look at those today. We'll begin where we've already begun, and that is with this shape of the continents. If we look carefully all over the Earth, coastlines appear to fit together, like this part of South America and this part of Africa. And so that becomes evidence number 1, the apparent fit of the continents, that the coastlines appear to fit together like the pieces of some sort of giant puzzle. But of course, this was just a starting point, and so Wegener continued his research. The next thing he dove into involved life. Wegener began to study fossils of ancient creatures, and more importantly, where those fossils were located. Take, for instance, this creature, an ancient freshwater reptile called a mosasaurus. Interestingly, if you look on all of the continents and land masses of Earth, fossils of the mosasaurus are only found in 2 places. These include the very southern tip of South America and the southern tip of Africa. Now let's think about this. How could this be possible? We know the mosasaurus could not have evolved in one location and then traveled to the other. It was a freshwater reptile and therefore could never make the journey through the salty Atlantic Ocean. And so that idea is out the window. Another idea is that Perhaps the same exact creature evolved in the same exact way at the same exact time in two locations that are separated by thousands of miles. But to Wegener, that was unlikely, if not impossible. And so what he concluded was that during the days when the Mesosaurus thrived, Africa and South America were not separated by an ocean, but rather they were connected as one landmass where the Mesosaurus could roam free. And then at some point later on, those landmasses with the remains of the Mesosaurus were ripped apart and separated by the ocean as we see today. Now this seemed like a radical idea to Wegener, until he began to look at other species of living organisms from the time. And what he found was much the same. There were all sorts of creatures beyond the Mesosaurus, like the Sinomythus and Glossoteris and Lystrosaurus, who all showed very similar, unique fossil distributions, as seen here. And strangely enough, if you reassemble the continents according to their shapes, the distribution of the fossils makes perfect sense. And so this becomes piece of evidence number 2, fossil correlation, or the matching up of similar fossils found in distant locations. At this point, Wegener is excited because his theory is coming together and his ideas seem to have a lot of support. And so he set off to find even more evidence. And he did so by studying geology, or rock structures. Very similar to what he saw with fossil distribution, he saw with rock distribution. In fact, if you look at the mountains of the modern-day northeastern United States, they are the exact type and age of rock found in the mountains of the UK and northern Scandinavia. And so Wegener said to himself, could it be that the same exact rocks formed at the same exact time, but in very different locations? Well, it is possible, but it seems unlikely. And so what Wegener concluded was that those rocks formed at the same time in the same location. And then that area was torn apart by the motion of the continents, carrying those rocks to the distant locations they are in today. And so this becomes evidence number 3, rock and mountain correlation, or the matching up of similar rocks from distant locations, proving that they were once together. And finally, his 4th piece of evidence is probably the most compelling of all, and this involves a look at the past climate of the Earth. So Wegener studied things like glaciers, and what he knew was that when glaciers move over the surface of the Earth, they leave behind evidence in the form of these glacial striations, or deep scratches in the rock, that show the direction the ice moved as it dragged over the surface. Now, interestingly, if you look at where on Earth we find glacial striations today, they're located in areas like the Amazon rainforest on the equatorial South American continent, and the hot, sticky jungles of Central Africa. Now, of course, these are places where you could not find glaciers today, simply because they're too close to the equator and getting sunlight that is too intense and hot, preventing glaciers from forming. And so what Wegener concluded was that these areas were not always near the equator, but rather in the past they were located closer to the poles, where a colder climate could exist and support glaciers. Similarly, Wegener looked at rocks like bituminous coal, which is a sedimentary rock that can be found on the New York State Earth Science reference tables. You can find this table at this link. Bituminous coal is a sedimentary rock that is made from compacted and cemented plant remains. But not just any plant remains, tropical plant remains from hot, sticky, humid jungles. Interestingly, if you look at the major coal deposits on Earth today, they don't fall in hot, humid areas, but rather they fall in frigid areas like northern Asia and Antarctica. So Wegener knew that if this was the observation he was making, this tropical coal being found in frigid places, that those places must not always have been frigid, and maybe in fact they were once located closer to the equator. And so this becomes piece of evidence number 4, paleoclimate data or past climate data, like finding evidence of coal in currently cold areas and evidence of glaciers in currently warm areas. And so these 4 pieces of evidence put together became the theory of continental drift, as published by Wegener in his book, The Origin of Continents and Oceans. Unfortunately, there was one thing that Wegener could never wrap his mind around, and that was what force could be driving the motion of the continents. He couldn't understand how it would be possible for huge land masses to actually move, considering the amount of force and energy required to do so. And without this explanation, his theory of continental drift remains largely rejected in the scientific community. In November of 1930, while on a research expedition on the ice sheets of Greenland, Wegener froze to death. His body was found in the ice months later. You can still visit a cross that marks the site of his death, frozen on the ice sheets of Greenland. The story of Alfred Wegener is a tragic one. It's the story of a great scientific mind who was ahead of his time, but died before he reached his true potential. Modern geologists owe to him their understanding of how the Earth actually works.
Examine the edges of the continents. So here we're going to look at the edges of the continents. Are any patterns observed? So here you can see the most evident pattern that South America fits perfectly together with Africa. You could type that there. What inferences can be made about the patterns observed? You can infer that these continents were once joined together, and you can type that there. Examine the fossil evidence on the map. So here's South America, here's Africa, and this fossil evidence is indicating that both these places have the same fossils. So you can observe that both South America and Africa have identical fossil species. What inference can be made by examining this fossil evidence? So you can infer that these two continents were once joined together where this fossil, this Mesosaurus, could freely roam, because the ocean is too vast for these Mesosauruses to swim across, or it was impossible for them to do that. So only one can infer that these two continents were joined together. You can type that there. Examine the map. Consider the glacial evidence. So here we can see that South America, Africa, India, Australia, here we all have these glacial evidences here. The lines on the map indicate deposits left behind by glaciers from 250 years ago. What inferences can be made about the glaciers and how the material they left behind when they recede provides clues about the location of the continents? So we can see here that in the past it was much colder than it is now, because we know that South America and Africa, these places are much warmer than they are today. So these glaciers have receded and left striations on the rock, indicating that these areas were once much colder than they are today. So we can say glacier striations found in warm areas were not possible today. Examine the age of the rock layers. The image shows the center of the Atlantic Ocean along the mid-Atlantic ridge. Measurements of the age of rocks were taken along the center. Age measurements were also taken every few miles on both sides of the center. The area along the mid-ocean ridge is highly active with volcanic eruptions. What patterns can be observed? So here along the mid-ocean ridge, you can see this goes all the way down the Atlantic. And so what you can see here is a divergent boundary where plates are moving away from each other, and you have lots of volcanic activity, magma coming up and making new Earth. What inferences can be made about your observations? We can infer that the newest Earth is here along the ridge, and it's moving outward in both directions. So the same rock is being produced, but some is going right and some is going left. So you have your new rock or new Earth along the mid-ocean ridge, and then Earth further from the mid-ocean ridge we can say is older. Examine the location of earthquakes. So the map shows the location of earthquake epicenters over the last 30 years. What connections can you make between the locations of earthquake epicenters and plate boundaries? So you can see clearly where these plate boundaries are, and all along these plate boundaries are where you're going to find earthquakes and volcanic activities because the plates are moving. So where the plates are making a border of one another is where you're going to have those earthquake epicenters. Examine the convection cells in the mantle. Remember, the upper mantle is made of rock that's not truly solid, so it can behave as a liquid. When heat from Earth's core reaches the semi-solid rock, the material rises. When the material reaches the underside of the crust, it cools and begins to sink. In this way, convection cells create beneath Earth's crust. What inferences can be made about convection and plate motion? So what you see here is the hot mantle is rising and it's pulling the lithosphere, the crust, as it moves. So here you have a mid-ocean ridge, and part of the plate is being pulled to the left and part of the plate is being pulled to the right by these convection currents underneath that lithosphere. So we can say that we can infer that plates move due to convection that's happening in the asthenosphere, this rising and sinking of magma. And here's a beautiful video where you can see that mid-ocean ridge, and you can see that part of the lithosphere is going to the right and part is going to the left because of this motion, this convection that's happening underneath there.